Oh, it's like, okay, so this is our second time meeting. The first time we had a different name, but now we're in GPU mode. So thank you so much for coming. So really the theme of today is I want you all to come away with like interesting problems to think about for the year and like interesting colleagues to work with. So that's why our very first speaker is going to be Christos Kozyraki. The reason why we wanted Christos to speak is typically most people tend to be experts at one or two things. Christos has like basically made foundational work in like transactional memory systems, cloud computing, energy efficient systems, ML for systems, simulation tools. So we really couldn't, Vikram and I couldn't think of anyone who's more full stack. So yeah, without further ado, Christos, please. Thank you so much.
All right, good evening, everybody. It's a great pleasure to be here. Thanks, Vikram and Mark, for giving me the opportunity. So I typically give talks about detailed researchy topics, but it's Sunday evening, 7 p.m. Some of you are holding a beer in your hand. So I thought that let's talk a little bit higher level about a broader topic that may actually impact your life. Where is hardware heading, and what does it mean for people who are developing software? So let's dive into that. I've been involved with computer architecture research for about 30 years now, and I'll tell you this is the most exciting times I've ever seen. And it's exciting because it's the best of times and the worst of times at the same time. We are having major challenges. We're going to talk about some of them in a second. But at the same time, it's the fastest I've ever seen new ideas being introduced to products. So things are moving really fast. We can actually impact hardware products really quickly. So let's dive into this thing. Let's start with the good news. So this is a graph I borrowed from Bill Daly. It shows you what's the evolution of integer rate performance of GPUs over a period of 10 years. And if you see there, it basically says that it's scaled by about 1,000x. Now, this is the original Moore's law, 2x per year, as good as we ever had it, right? And it's expected that Blackwell is going to be even better than that. And you're going to hear a lot about Blackwell this week anyway, so I don't have to go into too many details. So things look great. And if you don't want to talk about bad news, this is a good time to take your beer and go outside and enjoy life, because the rest, the next 5 or 6 slides are going to be a little bit depressing. All right, so why am I saying that? So any performance improvement we make stems from improvements in transistor density, the original Moore's law, right, the real one. Okay, so this is a graph that I generated with public data about how TSMC processes have been shrinking over the last decade. And things are still shrinking. It's still an exponential, right? So we're not yet at the point where steel and cement are. The bad news is that we're at about 10% per year, maybe 20% per year. It varies a little bit, but we're way below the 2x that we expect. So things are scaling, but nowhere near as well as we want them, right? Now, the other thing to keep in mind is that Moore's law was never just a technology thing. It was always an economics argument. So we were expecting that every year we'll pay the same money and we're going to get a chip which is twice as capable, twice as many transistors, hopefully twice as much performance. What these two graphs are showing you here is that this doesn't hold anymore. The left graph is telling you that transistors are getting more expensive. So in order to get a wafer with 10%, 20%, 30% more transistors, you now pay more and more every time. The right graph, it's showing you that not only the transistors are getting more expensive, but you also have more money to develop it. This is basically how the NRE has been scaling over about a decade. And if you look really closely, that orange part that's getting bigger and bigger is basically all the software that we have to develop to make sure that these interesting but weird chips are useful to somebody, or the libraries, the kernels, the compilers, and so on. Now, these graphs have profound implications for the industry. The first one tells you that the chips are going to be deployed only for really high profit margin applications, because the transistors are getting more and more expensive. And the other one is telling you that we'll only deploy them for really high volume applications so we can amortize the NRE. So this may change our field significantly, but since all of us are working on AI, which is high volume, high profit margin, we can ignore it for a while. So we can move on. Okay, so let's go back to technical issues, not economics. The biggest pain for architects is the fact that all the chips are power limited. Okay, so what this graph shows you is that over time we're improving in density, But because we can no longer scale the power supply voltage that we feed these chips with, we end up with constant power consumption per transistor operation while we're squeezing more transistors per unit area. So over time, we're getting the power consumption per square millimeter or something like that to keep going up and up and up, right? And that limits basically either the number of transistors you're going to pack in the chip or at least the number of transistors you will use concurrently at any point in time, right? So many things like what people call dark silicon or low utilization of transistors are popping up. And this is basically what has been changing architecture for the most part. Okay, we're going to get back to this in a second. Now, there's a bunch of other problems that I don't have time to go into. Memory is not shrinking anymore. So if you look at the SRAM, DRAM, and NAND cells, they're scaling by a tiny bit, so not good enough for what we really want to do. Okay, that's a problem. We're going to talk about the solution in a second. And even interconnects are getting difficult. You have to pretty much choose between low energy, low latency, or long interconnect and dense interconnects. You cannot have both at the same time. And that creates all sorts of interesting design issues. You have to use multiple interconnects, optimize across them, and so on. All right. So by now, you're probably wondering, OK, that sounds really bad. OK, things are scaling slowly in a very weird way, power limited, memory doesn't scale, interconnect doesn't scale. How exactly did you get 1,000x while all these things were going on? All right? So let's try to summarize what computer architects have been doing for over a decade in 2 slides. So, you're under your advanced computer architecture class in 5 minutes. All right? So you can give me your Stanford tuition a little bit later on. So basically, here's what hardware people observed. But if power consumption is constant, then we have to start thinking about the components of this that contribute to power consumption. And there's 2 things that you have to worry about. The one is how much energy you spend per operation, and the other one is how many operations per second you're actually executing. We want that green term, operations per second, to be really high. That's performance, right? And since power doesn't get better because of process technology, we have to figure out architecturally how to decrease the energy per operation. So what hardware people have been doing for 10 years is looking really hard and asking the question, can I decrease the energy consumption of this operation, whether it's a load and store or a matrix multiply operation? Now, peeling the onion 1 layer, what we typically do is create tables like this. This one I borrowed from Google folks, which shows you basically the amount of energy in relative terms that you have to spend to do various operations, arithmetic, decode an instruction, access memories of different types. And if you stare hard at this table, you will get every single good idea that came in computer architecture in the last 10 years. It's that simple. So if you look at the top side of the table, it basically tells you that the narrower the arithmetic you do, the simpler the arithmetic, the more energy efficient it is. So guess what we did? We basically told everybody, don't do 64-bit floating point stuff. Do 16-bit floating point, or 8-bit floating point, or 4-bit floating point, or maybe your favorite narrow integer thing. And then, of course, we've got software people to do compilers and libraries and algorithms to accommodate for that. That has been a major win in modern computer architectures. Now, the second thing that we observed is that we want these chips to be programmable, but the overhead of decoding, fetching, decoding, and controlling every instruction is actually quite high. And if all you do with an instruction that you execute is one floating point multiplication, you just don't amortize the cost of this fundamental unit of programmability. So basically, we turned around and said, don't use instructions to launch individual additions or multiplications. Use instructions to control a much bigger amount of work. A whole vector operation, a whole matrix multiply operation. In this case, the energy consumption stays the same, just amortize it over tens, hundreds, thousands of operations, and the cost is much lower. All right? So this is the second thing we did, matrix multiply operations, as you know quite well from modern GPUs. The last thing is we looked at the energy that goes into the memory system. And long story short, the smaller the memory that you're accessing and the closer it is to your compute unit, the lower the energy that you have to spend. So we started building hardware and software to make sure that we minimize how much data you use or maximize how much you use data so you don't pay the high energy of accessing off-chip DRAM as often. Right? So that's it. That's all computer architects have been doing for 10 years in one slide. Simple enough, right? All right, so let's go back and see how exactly it worked out for the GPUs that we discussed a few slides ago. So if you look at where GPUs got their 1000x, about 10x was from these custom instructions, matrix multiply operation, matrix vector operations, and so on. Another 10 to 30x from using Arora arithmetic, floating point 4, floating point 8, and so on. About the 2x more recently from sparsity. And at the same time, we got about 3x from clock frequency, it went up, and about 2x from increasing the amount of silicon area used and increasing the power consumption of the GPUs. Right? So the GPU power consumption started from a couple of 100 watts, and now it's 1,000 watts, and looking up. Now, all these things, of course, required a huge amount of software work, as you know pretty well, and even algorithmic work to be able to actually make sense out of this thing. Think about all the algorithms you know for quantization to make sure that you take a neural net that was trained in 16-bit or 32-bit arithmetic, and you can do inference at 4-bit of your favorite format. All right, great. Now, in terms of the memory system, the main thing we did is we squeezed things closer together. So we made sure that we don't go off chip or off package to be able to access our data. What we did is we put on the same package the compute and the memory, so they can communicate through a quite wide interposer. And for the memory itself, we just stack it on top of each other, which is great. We don't know how to shrink DRAM anyway, but we can stick more chips on top of each other. So this way we can get more capacity and lower power consumption for the high bandwidth that we need. And it turns out that this idea is actually pretty good and it's going to keep scaling. So the graph on the right tells you that TSMC expects that we can increase the density of these 3D stacks looking forward. So we're going to be doing more of this for sure. All right, so of course the obvious question to ask is like, okay, fine, scaling looks bad, but we played all these tricks and we got 1,000x over 10 years. Can you get another 1,000x over the next 10 years? Because if we can't, then we're in trouble, right? We're back to the 10, 20%. So let's go back and revisit what we can do looking forward. There is a bunch of things that will come from technology. So 3D stacking will keep going, both denser and more aggressive 3D packaging. Potentially we'll start 3D stacking of logic itself. And at some point, we're going to have co-packaged optics, so we can go straight from one chip to another using optics without ever having to go off-board in a non-optical way. That's great. It will happen from technology. We'll take advantage of those. Now, let's go back to the ideas that I told you will contribute to the 1000x and see if they can work going forward too. The first idea was more complex instructions, and that's kind of mined out. I'm not saying we won't do matrix multiply or instructions like that anymore. All I'm saying is that the efficiency we got from them is done. If you look at what is the overhead of launching an instruction these days, it's about 10% compared to the fundamental energy of actually doing the math that the instruction defines. So we'll keep doing this, coarse-grained custom instructions. They won't contribute to anything more than what technology offers. All right, so we've mined that out. Narrower data types, we'll keep doing this. We're getting close to the end, right? Like we're at 4-bit right now. We can go a little bit more and get ternary neural nets, so down to 2 bits. It won't get that much lower than that, right? So we've got another 2-4x there. That's it. We're done. Now, sparsity is interesting. So sparsity, we just have started. We've done structure sparsity, which is a little bit easier, right? There is also this thing called unstructured sparsity, where in theory, it can give us huge benefits, especially in the memory system, where we need it the most. The catch is that it requires much, much work from software people and algorithm people, and there's this chicken and egg problem, right? So if the hardware is not doing sparsity, unstructured sparsity really well yet, then people don't do algorithms for it. And if people don't do algorithms for it, then hardware people are not motivated to do the hardware. And we have to figure out some way of breaking that deadlock. And then finally, we have to do much more in terms of data flow. Sure, putting the DRAM on the same package with the GPU has contributed a lot, but if you look at where power goes, it still goes mostly communicating between the DRAM stack and the GPU on the same package. So we have to figure out somehow to get even better with data flow. Now, what do I mean by that? Here's a bunch of ideas that you can imagine. Avoid data movement altogether. We need to start thinking really hard about, do the compute exactly where the data is. Now, for you, it means that you have to start thinking about where's my data and how do I basically program the fact that I need to send the computation there. And for us hardware people is we have to do some fine-grained integration between memory modules and compute modules. The next idea is minimize data movement. Compress, deduplicate, filter, whichever way you can. Just make sure that you minimize the information that's floating around. Next is amortize data movement. If you're going to move data, do all the computation you can imagine for it. So you may load some data, calculate all sorts of embeddings, all sorts of interesting computations, even if you're not sure if they're going to be used later on, because it may be much more beneficial than loading this data 2 or 3 times later on when you know that's needed. And then finally, this is a good time to start thinking about trading off computation for communication. It's much, much cheaper to do math twice or 3 times rather than actually load the data a few times from far away. So we have to start thinking about algorithmic and programming support to be able to actually trade off computation communication. Now, if you look at the hardware that would most likely come your way because of all this, is we're going to start integrating compute and memories in a finer granularity and expose to you much more about the hierarchies, the memory hierarchies, and the interconnect. Now, I know that it sounds scary, but this is a good time to start debating about what's the right interfaces so that programming is not completely impossible for this quite complicated way of thinking about hardware. It's going to be a good thing to discuss in this forum. All right, the other thing that's changing in hardware is the deployment unit for hardware. And things are moving towards the direction where we try to deploy bigger and bigger things, such as the NVL72 shown here. Okay? So this is an unbelievable, hardware achievement, like trying to pack so much memory, flops, and terabytes per second of bandwidth in one box. Now, the reason that people do this is not just because it's an impressive unit of hardware. Once you integrate vertically everything within a refrigerator-sized computer, you can actually make sure that you don't pay significant overheads for all the communication capabilities and all the memory capabilities you have there. So some vendors want to be able to engineer things like that, to be able to trim all the fat and all the energy overheads or latency overheads out of the systems. So we have to go in that direction. It's not like we can avoid this, and it's just been done for business reasons. So what does this mean for the software side? It means a couple of things. First, if you think numinous has been ugly in whatever 2-socket or 4-socket CPU system you ever program, this is going to be worse. You're going to have NUMA on a single chip, a couple of chiplets within a GPU, NUMA on a board, NUMA on the refrigerator, and it's going to be heterogeneous. Like you're going to have multiple types of compute, you're going to have multiple types of memory, and somehow your software has to be able to make sense of this thing and get the best possible performance out of the system. It's not going to be easy. It's a good time to start debating about what interfaces work, where did we get the hardware kind of right, or where do we need to steer it in a slightly different direction. The other thing that is interesting, if you flip it the other way around, is that if we have to design systems like this, highly integrated, because that's the way to get the efficiency, that means that we need to get all the applications ported and efficient on this kind of a system. And AI, everybody's motivated to do this thing right now. I think it has to be done for pretty much everything that's important, including any kind of database and any kind of analysis you can think about. Like, you like it or not, that's the future of hardware. We need to make sure that a database analytics work for that. I spent the last few months talking to database people about why don't you use GPUs or systems like that for databases. Mostly researchers, but you still get the same answers probably that you get from product people. And here's the list of things that they typically tell me. This is all the reasons why they don't want to touch a GPU for databases. So let's go down the list and see what holds and what doesn't, right? So the first thing tends to be it just doesn't have enough memory. So GPUs right now, because of inference, are packing as much memory you can put in a package, okay, in the hundreds of gigabytes. Like they're really pushing the limit of integration technology. Nobody else can pack more more memory on a chip. And then you've got terabytes per second to whatever external memory system that you want to build. And of course, you can build anything, right? Like just connect it to NVLink and you're there if you don't like the one that's there already. So in terms of memory, you have as much capacity as possible locally and then enough bandwidth to go off chip so you can cross this out. The next complaint tends to be, yeah, I like the bandwidth, but I'd like to have really fine-grained access to my data. I'd like to do pointer chasing to 8 bytes at a time, which sounds really great. I'd like that too. It just cannot happen. There's this thing called the Little's Law, which basically tells you that as the bandwidth goes up, if you want to have access to fine-grained data, you have to have a huge number of understanding addresses. And that's really difficult to implement from the point of view of hardware. If you want terabytes per second to your data, you need to have thousands of pending memory accesses, which is really difficult to issue them from the software point of view and imagine from the point of view of hardware. So whether we like it or not, fundamentally speaking, if you want terabyte per second level bandwidth or hundreds of terabytes per second, it's going to be some coarse-grained access. We can debate if it's 1 kilobyte or 4 kilobytes or something else, but it's going to have to be coarse-grained. So let's cross that out too. There's a lot of discussion about, hey, look, I like memory, but I also like disks and flash devices, and the integration not great between GPUs and storage. Vikram, one of the organizers, can do a lot about how to do NVMe correct with GPUs, and it works actually quite well, so I'll cross it out and leave it for him to give you a talk at some other point. There's also a lot of work going into how you make networking for GPUs much more flexible, so that people can come in and customize small aspects of those. Talk to me offline over drinks. I'm glad to tell you a few things that we've done in research, but many of these are showing up in products as well. And then the final thing, which I've got to give it to them, they have a point there. They say, look, the data types that we've, introduced into GPUs for AI are not necessarily the best for databases. And there's two ways to say this. One is, actually, you can do a lot of stuff even with the net of data types that you have for AI. Okay, and many people have shown that you can take, let's say, 4-bit arithmetic for AI and use to do wide arithmetic for crypto. Okay, you can synthesize wider numbers, smaller numbers. But you can also say the other way around. If you go to any GPU vendor and say, look, I know how to port my application to your big system, but you have to provide support for some new data types, I think most GPU vendors will be open to this thing. So I think that's a good debate to have, and if you need a new data type, it's going to be the easy thing to discuss there. Now, from my point of view, the thing that's really missing is not this hardware stuff. I think the thing that we're missing is some good intermediate representations to be able to compile SQL down to these things. It's not going to be in one step. There needs to be something like MLIR for this space. Some operator generators, some optimization frameworks, we need that middleware infrastructure. I think that's the real thing missing there. The hardware will evolve as is needed. Now, finally, one last thought. As we are going into optimizing software for systems like NVL72, it's kind of like a warning. It's very easy to look at something like NVL72 and say, look, it's a supercomputer, right? It's a refrigerator-sized supercomputer, and we have taken supercomputing classes. We know about supercomputing software. We've been borrowing ideas for the AI infrastructure for a while. Let's keep going in that direction, right? It sounds great. And there's some really good ideas there, so keep doing this, but you have to be aware that there's also a slippery slope here. So let me tell you what. I started doing computer architecture research in the mid-90s. And at the time, the whole discussion was we wanted more compute capacity than what a single CPU can do, so we wanted to connect about 1,000 of them into one system. Now, the predominant approach at the time was to build supercomputers or CC/NUMA servers. These were these custom, amazing machines, a lot of proprietary hardware for the CPU and the network. And the whole idea was to take 1,000 processors and make them look like they have a single memory address space. So for the programmer, it's like one computer. You can do a lot and store everywhere, and it will work, right? Lots of interesting companies, Cray, Convex, and so on, Sahan, SGI, were building amazing systems at the time. And many people expect that these wonderfully engineered, really low latency, high bandwidth systems would dominate. What happened at the same time was a bunch of people, initially at a university like Berkeley, and then eventually companies like, Google and so on, basically said, you know what, forget that. Let's just get ordinary servers and connect them through Ethernet networks, tell everybody you are writing distributed software, and go for it. And it turned out that approach won. Okay, that's what cloud computing is right now with this Paliskara private cloud. It's the evolved version of this. It's not the same servers and not the same networking, but that approach won, even though everybody expects to be lower performance and much more difficult to use because you write distributed software. And it won because it was much easier to scale, more cost efficient, easier to do resiliency, much easier to program, it turns out. If you have a cell phone, Right now, you're using a distributed application running samples on the cloud. And even though we think distributed computing is difficult, somehow people figure out how to make every single app to actually have one of those in the backend. And then the thing which I appreciate the most, the performance portability and predictability is easier in this environment than it has ever been. Like, you write a program for Google's cloud, and then you take it to Amazon cloud, and performance is decent. It won't be super optimized, but it's kind of good. Okay, you don't have to rethink the program from scratch. Okay, now why am I telling you this? Like, other than tell you that I'm old. If you look at what we're doing right now, we're asking the same question, right? And instead of basically saying I want to connect 1,000 CPUs, we're saying I want to connect 100,000 GPUs, right? For a big training job. And if you look what people are building, the hardware actually looks like supercomputers. Okay, this is TPU, the 3D torus. If Simran Gray was to come back to life and he would look at the block diagram of the thing, he would get everything. That's exactly what he was building at Cray, right? And the NVL72 is not CC NUMA, but it's close enough to that, right? Like probably a little bit of freedom here. And if you look at the software that we're writing, it's big synchronous supercomputing jobs. And all sorts of things are difficult. It's difficult to scale performance, it's difficult, it's expensive, resilience is a pain in the butt, portability is strange, it's very difficult to take a TPU program and run it on a GPU, even across GPUs is difficult. And performance portability is just not there right now, right? So we are doing something wrong, which points to me that there may be a scale-out AI story somewhere there. We don't have to go back to 2-socket CPU servers. Now, we can still use this kind of hardware or some evolution, but we may want to rethink about how we build systems, both hardware and software, to go more in the scale-out direction than the scale-out that we are right now. Now, how did the scale-out people win in the 90s and the early 2000s? Here's what I think they did. The first thing is they spent much more time co-designing systems and applications that we are doing right now. So if you look at the database, for example, the kind of database that right now in the cloud, they're very different than the database in the 90s. Okay, they co-designed the distributed hardware and distributed software quite well. They designed for flexibility and customization from the very beginning. Networking, storage, resource management, they were all there and designed in a way to recognize the fact that you're not serving a single application which is static. Many things will change. You need to be able to come in and plug a new scheduling algorithm, plug a slightly different networking protocol for a different scale. And then finally, they designed for the realities of the large-scale systems from the very beginning. Okay, they didn't assume that everything is beautiful, homogeneous, and failure-free. Like heterogeneity, failure, stragglers, multi-tenancy, and massive data sets. They were building assumptions from the very beginning. Nobody tried to optimize one job as much as they could, just for the heck of it. So I think it's time to take this playbook and replay it, okay, and start having these debates about applications, programming interfaces, hardware. How do we move everything in that direction? Otherwise, we're going to have problems going completely in the supercomputer way going forward. There's a lot of people who are doing bits and pieces of this. We do some research around the bottom two and started to play a little bit with the top one. Glad to talk to you about all this stuff over here. Anyway, I'm going to stop here. So we have a little bit of time for questions. Thanks for taking the time to listen to me. Again, this is interesting times. This is hardware scaling, but we are running into a bunch of problems that will obviously change the software as well. It's a really good time to start having a debate about this is what works in algorithms, this is what works in programming systems, and let's couple it to where hardware is going. So looking forward to all your ideas.
People have any questions? Just raise your hand if you have any questions.
You did show the Moore's law scaling. So how does the wafer scale engine fit into that of hardware scaling?
The wafer. So at the end of the day, all of the chips start on a wafer, right? And everything shrinks at 10 to 20%. Okay. The thing that wafer scaling buys you is that you have 1,000 of them connecting, with cheap kind of interconnects as opposed to one that goes through an interposer or an off-package bandwidth. The issue with wafer scale or any approach like this is the following. If your application fits exactly the size of the wafer, this is magic, right? You have exactly the right amount of compute with the densest technology for interconnect. But if your application doesn't fit because it's too big, or can only take advantage of 1/4 of this, then you either, in the case that it doesn't fit, you're limited by the off wafer interconnect technology, or the other way around, you're way overpaid for what you're getting. So integration is interesting. Now, whether we should do bigger packages to do right now with multiple dies, or 3D or wafer scale, I think it's a good debate to have. But I don't think that just going wafer scale will solve everything. That's because you can guarantee that the applications fit exactly that size.
You gave for for scaling out CPUs and databases in the 1990s, right? So yeah, back then it seemed like you were running relatively lightweight programs, and so it kind of made sense to distribute a bunch of lightweight programs across several smaller nodes, and it kind of like I could see a much better value prop for cloud computing there. I'm wondering, when you bring this analogy to GPUs, I want to hear more of your thought process on what carries over, since, I don't know, I guess my mental model is more like, it's kind of the opposite, where we're running very large jobs, or relatively much larger jobs, that just straight up require, like the teraflops just straight up require like a rack, And so what does this like multi-tenant, like this distributed, what does this paradigm mean in this GPU sense?
I agree with parts of what you said and disagree with a couple of other parts. You're absolutely right that the works are different. We will not do exactly the same, right? Like we don't have to go to 2-socket servers and heavily flash drivers on the network and stuff like that. On the other hand, cloud apps were not small either. I haven't worked on Google Search for a long time, but I remember even back in 2011, 12, the minimum unit of deployment of Google Search was a few thousand chips. Like it wouldn't fit anywhere if you didn't have a few thousand chips there. So cloud also had big jobs, and somehow this distributed approach made sense. So it may be that in this incarnation we'll do more on the software side. Let's say we'll do more slightly less synchronous AI than we're doing right now, rather than the hardware side. But it's a good debate to have. I think that's the most important part here. Like, it doesn't have to be exactly the same at the end. I don't know who's speaking, who asked the question, and the microphone's like somewhere in the back, yeah. Yeah.
So yeah, I think my question is, I think somewhat similar in nature to the previous one, in that I would definitely say like this idea of kind of like more like asynchronous, like more fault tolerant, like I think everybody would love it. Like I think everybody working in the infra, like training these large models, would love to have like more highly like asynchronous tasks. I think the big challenge is just like this isn't what we have today with like these ML models. And so I think like from my perspective, I think the most dominant like bottleneck to kind of going towards like a more like commoditized compute type regime is kind of not on like the infra or software side. It's more on like the modeling side. Like you need to convince the ML researchers that yes, you guys need to like tolerate like asynchrony. You need to tolerate like non-determinism. You need to tolerate like faulty compute. And I think this has kind of been like a hard sell historically for ML researchers.
So I agree with you that it's not an easy sell. The one thing that we as systems people can do is we can do what I'd probably call as can do slightly asynchronous systems. Like we can tell the AI people, look, it's a mostly synchronous system, but every now and then I'm going to bend a few things to be able to get you cheaper resilience. And it doesn't have to be hog wild, if you remember that work from Chris and so on, where everything is completely asynchronous. It's going to be slightly asynchronous in very small and precise ways to be able to get, let's say, resilience to be cheaper. And these kind of ideas are easier to sell. And this is what, for example, like the scale-out community has been doing with databases and things like eventual consistency for quite some time. Like if you ask the programmers of databases, they would love to have fully synchronized systems there as well. And somehow they learned that eventual consistency can be managed, right? And things advanced. But I agree with you, it's not going to be an easy sell. Maybe, the catch is that, we cannot wait for this thing to become a crisis, because hardware takes 3 years to build, right? And if it becomes a crisis, then it's going to be 3 years. So we need to have this debate now, so that by the time that is actually needed, we have something there, hardware and system software.
Yeah, I would agree with that. I think it's just like, it's very like in the world where people are spending like billions of dollars on like these like ML training runs, I think it is a little bit of a harder sell to say then please introduce this extra like form of asynchrony or staleness.
The good news is that some of this is public on its own. So if you need 100,000 chips to be able to do your training job, for most people that means 2 data centers, or 3 data centers, or 4 data centers. And even if you have dark fiber between those, typically you cannot control synchronization of that thing as well as if it was in the same building. So some parts of it are creeping in anyway, so they have to think about it a little bit, so maybe we can squeeze in some ideas with that. So that may be one way.
Yeah,
but you're absolutely right, it's not an easy thing.
All right, I think if people have more questions for Christos, please meet him after the happy
Absolutely,
hour.
yeah. Thank you.
We're going to have to go to the next talk. Thank you, Christos. Thank you so much. That was excellent. No, it's fine. Okay, so for our next talk today, we have this like cool-looking logo, but we're going to give an update that's kind of cute. And we're going to talk about the Popcorn project. So the Popcorn project has been a collaboration between like many developers from GPU Mode, from Stanford, from FAIR, from PyTorch, to effectively build like an expert-level GPU programmer. So fundamentally, like even from the early days, the reason why CUDA mode at the time was created was for me and Andreas to learn CUDA. So the fundamental goal was to make GPU programming more accessible. And we still feel like GPU programming is still too hard. It's still too damn hard. Effectively, even the single most important kernel like written in human history, like Flash Attention, still took 2 years to write performant versions for H100. And this is, again, by some of the most talented kernel developers that we have today. And this problem gets worse. Like, effectively, if you sort of like look at like different kinds of models that people may want to run, you effectively completely bottleneck the pace of ML research, primarily because we don't have enough human talent to go make all these things fast. So the idea was we would want to create in the open an expert-level GPU programmer that anyone can use or reproduce. So basically the model is freely available, the data, the recipe, anything you want, we make it free to everyone. Okay, like I had some conversations before during like over there, which was people like, well, if I use Claude or A1, they like frequently hallucinate like things. They're not sure if Triton is CUDA or if it's like or if it's PyTorch. And fundamentally, we have this eval called KernelBench, which really shows us that like all existing models are effectively bad, and it gives us like very concrete data as a way to measure progress. So this work was led by Anne and Simon from Stanford, and it's like quickly become like the main reference like benchmark people use for KernelLLMs, like whether it's like Sahan or many other similar projects. So really, the main hypothesis we were trying to answer with this work is like, why do existing LLMs suck? And our primary hypothesis going into this was because of data starvation. So how do we solve this? So the first thing we're releasing is called KernelBook. KernelBook is the largest kernel data set on Earth. Effectively, what we did with this is we parsed all of GitHub. We took all Torch code from it. Torch compiled it and got pairs of Triton code and like released it. So these are real models. We also parsed like all Triton kernels that are on GitHub. So this is like about 2,000 of them. So all of these are examples with permissive licenses. So if you'd like to study them or use them to train your own model, we now have like a new Hugging Face repo, and this work was led by Sahan, who will talk more about this. The second thing was, well, still, like if you actually look at KernelBook, you'll notice that there's like a lot of data is duplicate. So it's not the highest quality data. So what we've been working on is KernelBot, and what KernelBot is it's effectively an engine for us to gather more high-quality human data. We market it as like a LeetCode-like platform for people to compete on GPU kernels, where like one reference is like, let's say, the PyTorch code, and then you write like a fast like CUDA or Triton or whatever implementation that you want. And we got like essentially free compute from many of our amazing sponsors like Modal, NVIDIA, AMD, Nebius. And what was wild about it is like even on a practice round on like toy PMPP problems, we ended up seeing over 2,000 submissions in a couple of weeks. And effectively what we'll do is we're going to host like multiple rounds of competitions, like between 5 to 6 a year. And every round will release all of the submissions as a permissive data set for you to study or train an LLM on. And we hope this accelerates the quality of like kernels on the internet. So this work was primarily led by a lot of people in GPU mode, from folks that aren't here, like Matej and Eric and Ben. but you'll hear more details from Alex later today. So again, this is like the fundamental formulation of the data set. Like torch compile has this like awesome flag called torch logs equals output code. And it can give you like Trident code for any PyTorch code that you might write. It doesn't look this nice, but there's a couple more tricks that Sahan will go over to show you how we made this happen. So the main contribution I want to talk about today is like really KernelLLM. So this is a state-of-the-art like SFT model. What we did was we took the Llama 3.1 8B baseline, which is just terrible. And after SFTing on this data, it starts to get like 17 kernels that are correct on KernelBench. And if we sort of do like a very toy reasoning loop, as in just a pass at 20, we end up with an 8B model matching the performance of a 670B model with DeepSeek R1. So this is really just the start. And there's a lot more we need to do beyond translation to make this actually work. There's like other tasks we're investigating, like minimal edit distance with maximal performance gain, kernel discovery, like discovering the next flash attention, auto-tuning heuristics, and fundamentally, like let's say you create a kernel, like what is the bar to actually merge this in a framework like PyTorch, and then finally like abstraction discovery. So these are like all hard research problems, and if you're interested, please chat with us at the happy hour. One we've made progress on is abstraction discovery. So the primary hypothesis here is that abstractions that are easy for humans are likely also to be easy for LLMs because they'll have a short lines of code, they'll be easier to reason through. So we're really excited to share some of the progress we've been doing with Thunderkittens, where like it's ended up becoming like a very easy way for, especially for unconventional architectures, for things like based attention. You can see like 10x speedups over like a Trident or CUDA baseline with a library that's like about like 1 megabytes in size and that you can read in an afternoon. So yeah, overall, like our contributions here were KernelBench, which has quickly become like the reference kernel benchmark data set, KernelBook, the largest kernel data set ever published, KernelBot, like a viral platform for competitive GPU programming, KernelLLM, a state-of-the-art SFT LLM Trident programmer, and finally Thunderkittens, a simple library for blazing fast kernels. Thank you. All right. So without further ado, we're going to tell you how we actually built this. So I want to introduce like Simon, talk about KernelBench.
Okay. Hey everyone, my name is Simon. I'm a PhD student at Stanford. And we've been building KernelBench to see if the LLMs can actually write GPU kernels. We actually been thinking about this problem for a while. We started doing this in the GPU mode hackathon last September. And with the thing to be concrete, what we want to do is give a PyTorch architecture that describe what are the operators we want to write in this and our module. We throw this to a language model, and wouldn't it be great to take some of the operators, convert them to fast custom kernels, either in CUDA, which we started doing, and then we added Triton recently with the PyTorch team. So the natural problem is that what kind of problems or workloads should we run this task on to evaluate the language model's capability? And this is how my KernelBench, which is a collection of 250 problems in PyTorch across 3 levels, and I'll tell you what they are and why are they hard. So level 1 is a bunch of simple single kernel operators, like a matrix multiply or convolution. These are very hard because you already have very highly optimized hand-written kernels to compete against. And level 2 takes a bunch of them together, add some nonlinearities and different combinations. This is to test the ability of the LM to do kernel fusion, which is really important because you want to reduce memory traffic, don't want to write back and forth. And level 3, you go beyond the few operators, you go full neural network architectures like Vision Transformer or Mamba. And this is very challenging because it's a very long program, and there might be some optimization in the algorithm that you can do. So we take these state-of-the-art LLMs, we give them 250 problems, and we try to understand, okay, how do they do? And to do that, we care about correctness, it has to be correct, and how fast they are. So for correctness, we take the module, the reference module in PyTorch and the generated kernel and the PyTorch program. We run them the same input, randomize a couple times, and see if they match. And then we measure the walk clock time to compute the speedups. So we care about, across the problems, the project data sets, how many of these are correct and faster than PyTorch. We care about eager mode execution as well as compile, but I'll show eager today. So actually, they're pretty bad right now. They don't get them really correct, and if you get it correct, it's pretty slow. And across KernelBench, you get about, the frontier models get about like less than 20% of the time faster than PyTorch Eager. They're also correct. And we barely see any kernels that are like 1.5x faster than PyTorch Eager, so it's really challenging for them. And we try to understand why they are so bad at this. If you look at the samples, they just generate like very syntactically incorrect code. Like they really wrong CUDA code, Triton code. They're unrunnable. Even if they're runnable, they're not logically correct. And if you tell them they're not logically correct, they don't know why. And I mean, it's already hard for me to debug a CUDA kernel. So I don't expect much of them. But even when they're correct and it's runnable, they're not that fast because they write very simple CUDA code. They don't really leverage all these fancy hardware features that's been coming out, like the tensor cores, the shared memories. We try to tell them to use them explicitly, and they are confused as well. So probably the reason they're really bad is not only GPU programming is really hard, it's just also very scarce in the training data. In like one of the most popular code pre-training data set, the stack, like less than 0.1% of the programs are CUDA. And for Triton, we scraped the whole internet. There's like 2,000 unique Triton code. And they're mostly like doing the same thing. But we're not hopeless. So KernelBench provides an environment for us to try new methods and see if we can actually make progress in the benchmark. And to do this, we have a bunch of ground truth signals that we can provide people to try their fancy new algorithms. For example, you can get the MVCC error messages for compilation errors. You can use our evals to check the outputs. You can use the PyTorch profiler NCU to get the operation breakdowns to figure out what's slow and how you can speed it up. We started trying a bunch of them in our paper, like we scale up test time compute, do repeated sampling, you do iterative refinement, use all these tools here and see if the LLM can improve itself. We generate a ton of trajectories, how they improve, and with labels of their speedups, and we release all of them a Hugging Face so you can do some post-training with them. So many ideas to try, and indeed, even the last months, this is all in February, there are work coming out on KernelBench from NVIDIA, from Meter, from Sahan. So feel free to get involved if you're interested. We're adding a lot of features to KernelBench. We just added Triton. We are targeting different hardware, different programming languages. If you have a cool problem and you want to add to KernelBench, let us know. If you think you solved it, let us know too. But check out our papers and and hear about the cool stuff we're doing next.
Hi, I'm Alex. I recently graduated from Princeton, and I'm one of the core devs on the KernelBot project, along with Ben, Matej, Eric, and Mark, who are all wonderful. So this project, as Mark kind of mentioned before, is sort of meant to be kind of like the Kaggle or the code forces of GPU programming. So this is kind of its first purpose, and the second part, obviously, is for data collection. So as Simon mentioned in the KernelBench paper, one of the main takeaways was that GPU code is a low resource language. And so if we really want to make this work for a KernelLLM, what we're probably going to need to do is gather some data for it. And the purest source of data in this form is human expert written CUDA code. So I really like this paper, the Limo paper that kind of came out recently. And it's very relevant sort of to this project as well. So even if we build out this platform, obviously it's going to be hard to scale this code very well. So one of the things that we're kind of banking on here is that given a model that has sort of a sufficient knowledge base, especially of GPU code writing, you can actually get away with training on a very small number of high quality samples. And this has been proven to work for competitive math and competitive programming. And I think structurally, actually, a lot of GPU coding is very similar to how you would write or how you would learn how to compete in these competitions. So I'm very hopeful with this idea as well. So I kind of want to talk also a little bit about how this competition has been going. For those of you that aren't aware, it's been running for roughly a month now on the GPU Mode Discord. And there have been no prizes. But so far, we've had over 2,000 submissions from a lot of people who are actually in the crowd, and so we're very thankful for that. And we've had a lot of very, very interesting and useful feedback. The other kind of thing that I want to mention here is that this entire leaderboard has been fully on Discord, so everything has been user submissions on Discord. And the other thing is that we know GPU evals can be a little bit finicky, and so one of the things that we're kind of hopeful for here is that we make this leaderboard kind of an iterative refinement process where we improve on the eval as time goes on, kind of like a living eval of sorts. So I'm really happy to kind of announce and talk about the real round one and kind of beyond. As Mark mentioned, we want this to be sort of a seasonal thing where new problems come out every so often and people can compete over them. So we plan on having real prizes that people can win, obviously. But another big change actually is in our practice round. We kind of released all the problems at once. And this is really hard for people because you have to context switch between different problems, and it's kind of a pain. So one of the bigger differences here is that we will be releasing one problem a week, and people can focus on these problems for a small set of devices. And scoring will be based on your rankings on each of these problems, and by the end of these, each of these problem sets, you'll get like a final ranking. So all of the problem sets as well will be somewhat themed and all somewhat related. And the other thing too is that for any companies or labs or individuals that are looking to suggest any new problems, whether it be related to like something that you want to do or just for looking for talented people to come hire, I think this platform is a great place to do this. So yeah, it's really, really easy to participate. All you have to do is join the Discord, which I'm sure most of you are already in. And you can just type one command. You basically just submit your script to the leaderboard. We have lots of very nice documentation. We have a website coming up, and we also are planning on doing CLI submissions. And actually, Charles and I today added B200 support just for the day. Only for today, though. Yeah. But yeah, so kind of the other part of this Limo hypothesis that I talked about is creating a model that has a strong knowledge base, and this is a little bit more related to what Sahan will be talking about with the KernelBook project. So.
Thanks, Alex. My name is Sahan. I'm a software engineer on PyTorch, and I've been working on KernelBook, or I guess the data side of Popcorn for a bit. We've been talking a lot about the data scarcity regime, so I won't go over it a bit more, but the point is we need more data. And to do this, we're doing two things. One, as Alex mentioned, is the kernel leaderboard, but it's still in its early stages. Please do round one. So we're still waiting on the data for that. However, we kind of asked what can we do? Is for kernel data, there exists Trine, and with Trine, a decent way of generating it is actually torch inductor. In fact, torch inductor is a pretty good way of learning Trine code itself. So we kind of had the idea is why don't we just take a bunch of PyTorch programs, which both exist online and we can synthetically generate, run it through torch inductor and see what comes out and try to train an LLM on that, which is the translation task we were talking about earlier. So this is kind of what it looks like. We take some PyTorch program, we put it in through torch logs, but you get a bunch of cruft, right? So you kind of need to scrape out all the cruft, guess the primals, do all that. And we kind of end up with something that looks nice, but more importantly, we kind of end up with a data set that looks like this. And it's also kind of important to mention we also need to maintain kind of a high quality bar, as in can we write unit tests for this thing, there's no graph breaks and stuff like that. And interestingly, when we actually go through about 140,000 programs on GitHub, we actually really only end up with a 20.5% yield rate. And even then, only 50K of these programs ended up being usable, even if the yield was perfect. So we kind of had to look at, okay, what can we do now? Because we thought that wasn't enough data. So Alex and Simon especially did a lot of work in synthetically generating PyTorch programs. What the work here was doing was we took a bunch of PyTorch operators. From there, we did some sampling as well as controlling by diversity. We asked an LLM, hey, create a PyTorch program from this, and hopefully it's interesting. And then from there, if it worked, we saved it. Otherwise, we threw it away. The really interesting thing here is because we had a controlled environment to create these programs, this increased the yield rate from 12.5 to about 75%, which through about 10,000 samples gave us about 7.5K synthetically generated programs. And we also have 18,000 programs that samples we have on GitHub. You can find these on the Hugging Face or GPU mode as well. Anyway, moving forward, there's a lot of stuff we can do, such as improving the yield rate or synthetically generating programs. But I think the really important thing to emphasize is the best data that comes from humans and you guys, and through the kernel leaderboard. And outside of like, as a data flywheel, like Alex and folks worked really hard on making this a really fun and seamless experience. So please like actually use this thing. It's like pretty fun to use, and it's meant to like be a very like community-driven thing to both test your CUDA skills and also learn GPU programming as well. And I guess this is enough yapping about data. Let's talk about what we did with it. And here's Zach to talk about the model we trained with it.
Thank you. Right, my name is Zacharias Fisches. I recently joined FAIR at Meta, and Mark approached us to train an LLM on the kernel data set that Sahan was building. And I have the honor to present the work that us at Stanford and in the PyTorch team and at FAIR did together. So the research question again is, why are LLMs so mad at writing Triton kernels? And we've talked about CUDA, but Triton I would say is even worse. And what do I mean by that? So we take the KernelBench Triton variant that we mentioned, and we just focus on level 1, the simple stuff, right? And all we ask is for correctness, and we take a state-of-the-art Llama 3.18b model, and it gets 6 kernels correct, right? And you think, okay, maybe that's not quite state-of-the-art. So let's go to GPT-4, DeepSeek, V3, these things, and we end up at 15 or 16 kernels that come out correct with almost like half a trillion parameters, right? And can we do better than that? Let's take a 2025 model, DeepSeek R1, and we go to 30, and using sort of the latest tricks in reasoning. And is that really good? Well, actually, no, that's really bad. Like 100 would be good, right? And there's 70 missing there, and we don't really know. It's probably not the number of parameters, right, that are too small for this. So what we're going to do about that, right? The first thing that we always do is we look a bit at related work. And so the folks at Meta, they basically run an evaluation study targeting, well, they were targeting CUDA as well, but they ensembled a bunch of state-of-the-art reasoning models from OpenAI and DeepSeek, added some scaffolding around it, and now the way they evaluate on KernelBench is they say, well, what's our pass rate if we spend, pass at $20 is what I call this, if we spend $20 of compute per kernel, right? Okay, fine, we can do that. Then our friends at NVIDIA, they also put DeepSeek R1 into a loop, and they used NCU output as like feedback from, let's say, as a verifier, and they took that feedback, fed it back into DeepSeek R1 to ask it for like improvements. That's also a way, something to do, and we do pass at 20 minutes per kernel, right? And then the folks at Sahan, I think they have one of the most interesting approaches that has been done. However, I think their results are a little bit work in progress right now because the optimization algorithms that they used were probably a bit better than the test cases that they had in some instances, but they're going to update this soon, and I think this is really interesting. And in a nutshell, all this related work amounts to is sort of test time augmentations around the problem, right? And so we wanted to answer the question, what happens if we train an LLM on kernel data, right? Our hypothesis is LLMs are highly data starved in this kind of low coverage regime, but I guess they can be trained. And so what we're going to present today is only the very first step in this direction and the very easiest thing you would do. So we take this translation task with the KernelBook that Sahan has introduced. We take the worst model, Llama 3.18b that I showed you today. We add a standard instruction fine-tuning recipe, and we will evaluate on the KernelBench eval task. And with that, basically, behold the KernelLLM. The results, I will quickly go through them with you. We jump from 6 to 14 correct kernels if we train on 6,000 samples, So we said, let's double that. Let's go to 12,000 kernels. We get 16 correct. And we said, let's double that again. But actually, with the way that we were creating the data set, where every kernel wants to be runnable, testable, verifiable, we ran out of GitHub. And so we added 7,000 synthetic samples as well and got to 17 correct kernels with this. And now let's take a poor man's approach at test time scaling and put this into a parset K loop. We probably have a verifier if we just run it on GPU and compare it to torch output. And so here, the baseline jumps from parset 1 with 6 to parset 20 with 14. Our trained model jumps from 17 to 30. And with that, we're basically matching a 2 orders of magnitude bigger thinking model, right? And yes, we need the verifier for our result. So we take silver and we leave the crown to DeepSeek R1 for today. And this project is far from done. I think we're only getting started, but we see the potential. There are real limitations here. So these networks make lots of trivial errors. They hallucinate APIs that don't exist, that never existed, where there's 0 Google results for. But they're good enough to fool the Google AI overview. But so if you want to learn about these hallucinations, just look them up. But anyway, also a more quantitative error analysis kind of shows that we can, with training on this kernel data set, we can move from like totally dumb errors where it gets sort of the Triton language incorrect. We can sort of move them to like, oh, the output was actually wrong, or there's a shape error in the output. So we can move from really dumb, you've never seen Triton errors, to like, oh, actually, these are the kinds of problems that you want to have, right, when you write Triton kernels. And then maybe we'll take it from there. And in summary, I think KernelLLM for the first time goes beyond test time eval tricks, even though I consider those tricks to be really important as well. We can, with a bit of an asterisk, maybe match the performance of a model that's 2 orders of magnitude bigger. And there's so much more left to do. We need to scale to better models, to larger models. 8B is not really where we want to stop. We need better data sets, right? This is just us creating the data set, but so please do use the leaderboard. And we do need to research methods on actually tackling speed up, because all we were doing today is sort of ask for correctness of the kernels, right? And we'd like to invite you to reach out to us. We want to share the weights as soon as we can. The recipe is standard. I'm happy to share that. So I think there's more than enough work for all of us. Please reach out and collaborate. And I think once we get this working, we'll be living in a whole new world. The one thing we cannot answer with this is whether Triton is actually a good representation for LLMs to write kernels or for humans. But here to talk more about it, please welcome on stage Simran Arora.
Hi, everyone. I'm Simran. I'm a final year PhD student with Chris Ray at Stanford. All right, so I'm here to talk about Thunderkittens, which is a set of programming abstractions for fast, simple kernels for AI workloads. And this work is with Benjamin Spector, my lab mate, Aryan Singhal, an undergrad at Stanford, and our advisors, Dan Fu and Christopher Ray. All right, so in my PhD, I've spent a lot of time, as have several of my lab mates, working on efficient alternatives to our de facto model choices in AI these days. So we have transformers. They're relatively expensive in terms of memory and compute requirements as a function of the amount of text we would like to process with them. In building some of these architectures, there's often been a gap between what ends up being theoretically efficient and what ends up being wall clock fast. So the two challenges of hardware-aware AI that we've largely come across are, one, some of the architectural choices that we make end up being sort of incompatible with what's actually quite fast on our modern hardware. So for instance, some of the parallel scan algorithms forego ability to use tensor cores, and some of the algorithms require sort of uncoalesced memory loads. The other challenge has been that of tooling and system support. So AI researchers, when we have an architecture or an algorithm, will sit down and write it in Python, so maybe PyTorch. And under the hood, for popular operations, PyTorch will already call to nice, well-optimized kernels. But for the diversity of these architectures and algorithms that we would like to be exploring, it's really not flexible enough. So, AI people, we like to think in Python. That's going to be, my premise here. And so, on that same vein, there's Triton, which is a Pythonic interface, as everyone here knows, to the hardware. But in providing this simplicity and more Python-like nature, forgoes some of the capabilities or access points that we need to get peak performance out of the hardware. For instance, fine-grained access over register memory or fine-grained control over asynchronous execution. On the other end of the spectrum, there are very high-performance, very widely used and successful libraries like raw CUDA or Cutlass. These, at the time of this work, which is over a year ago at this point, are largely C++ deeply nested templates, which are rather hard for AI people who think more in the vein of Python to quickly adapt. So that brings us to the question here, which is just an art project of what are the trade-offs between programming abstractions and how fast, simple, and broad a set of AI workloads we can support. And this, while directed towards helping people and AI researchers write kernels, could also provide implications for models writing kernels. And that interesting research questions there. Okay, so Thunderkittens, in terms of the results, I argue has picked a very interesting point in this trade-off space between abstractions and fast and simple AI support. So for relatively few lines of code compared to the C++-based libraries, Thunderkittens is able to provide competitive performance across different hardware platforms. And compared to Triton and the more Pythonic approaches that existed at the time, we're able to have comparable lines of code, a rough proxy for simplicity, not perfect, and still get quite large speedups in terms of teraflops there, while using a relatively small library size, again, just a proxy. And this is not just one hardware platform, but we have some Apple here, 4090s, H100s, and Ben and Aryan and folks have recently released B support as well. Just to briefly tell you what you'll see when you look at the repository and take a look at Thunderkittens, there's basically 3 folders in the library about types at the levels of basically memory, interface experience, and asynchronous execution management or compute. So on the memory side, the experience is a lot like working with tensors in PyTorch. So the basic data structure is a tile that's going to be some multiple of 16 by 16. And the memory layouts are sort of automatically picked for the user based off of the data type precision and the tile size at different levels of the memory hierarchy. Once you start thinking in terms of these tiles, you'll realize you want to run operations on them. So the set of operations are things like multiplies or add or X per MMA calls, which are very, very inspired by this Python philosophy and PyTorch and NumPy library functions. And finally, there's sort of a very opinionated choice of a kernel template that you can use to write these kernels, where sort of work partitioning, synchronization, and register reallocation, these sorts of things are taken care of for the user by the template, and the user just kind of needs to fill in a couple of slots here for their code using the functions and tiles I mentioned. All right, and with that, Thunderkittens has been, despite being more of an art project, has seen interesting adoption on the research side as part of published work, which was our ultimate goal. Folks I've never talked to have been using it to write some architectures here. It's also part of the GPU mode leaderboard, so you can use it to write your kernels and submit your kernels. It's being used in industry at a few places, including high-frequency trading and an inference company. And also more philosophically, it's been really interesting to see more and more Pythonic DSLs in the sort of year since we released Thunderkittens. I know like tiling, I heard Cutlass and Qt 4.0 are taking more of a Python approach. And so we're very excited to see if these types of new abstractions that are coming out can also simplify the experience of getting models to go and write CUDA code successfully. And then there are these research questions I mentioned about, are the abstractions people prefer the same as models, and how can we actually get models to learn to use these low resource tools? All right, and with that, I will hand it off.
All right, thank you so much, Simran. Yeah, I don't, it's fine, yeah. So yeah, like really the whole intent of this project was to be built in the open. Like all of our stuff is open source. We're already collaborating between Meta, PyTorch, Stanford, GPU mode. We'd love to include more labs, so please reach out to us like after happy hour. With that said, I think as Simran was talking about Thunderkittens, I saw like Vijay in the back sort of being like, no, but Cutlass is faster and simpler. So without further ado, Vijay, please come on stage. Thank you.
Thank you. Thanks, Mark. All right, while we wait for the slides to go up, I'll just introduce myself. And my name is Vijay. I'm on the Cutlass team at NVIDIA, and today I'll be representing the work of the entire team. We've been very hard at work for the last couple of years working on the next major version of Cutlass, and I am very proud to be able to announce this on behalf of the entire team today. So let me give you a sneak peek of what the future of programming in Cutlass looks like. And with that, I'm going to fail with the AV. Oh, the bigger button. That's right. So what do we want? What is the reason for Cutlass's existence when cuBLAS and things like that exist? Well, we realize that we want people to be able to write custom kernels for that big processor right there, right? It's the entire rack-scale computer that we want people to be able to program as a single distributed kernel and make it go at the speed of light and do whatever you need to do for your custom workload, right? So how do we achieve that? Well, Cutlass has been around for a long time. Cutlass was first released as open source back in 2017, and ever since then, its entire reason has been to enable people in the open source community to write custom kernels. It has nearly 4 million clones per month, 7,000 stars, and hundreds of contributors, right? People like TreeDAO have built Flash Attention 2 and 3 on top of it, and countless researchers do their pioneering ML research on top. And we want to make sure that people can continue to design new kernels as well as use Cutlass as a reference for off-the-shelf kernels, both at the same time, right? Cutlass is many things at the same time, and the idea is to expose a hierarchical set of primitives of these moving parts of a gem kernel or a convolution kernel targeting NVIDIA architectures so that people can use the highest level abstraction possible for the fastest time to solution, but then peel these layers away as they need to customize these kernels more and more. And that's where the elegance of Cutlass comes in. So we want people to be able to write custom kernels for complex processors like the Blackwell processor. And sometimes you really need to peek under the hood and understand deeply how the hardware itself works and what the instructions targeting that hardware look like. So what does the future of Cutlass programming look like? Well, Cutlass is going to the next major version, and it's all Python, baby. Here's how Cutlass code is going to look like in the future. You're going to be able to pip install a Cutlass wheel that's going to ship with a Python DSL and an MLIR compiler. You write kernel in a completely Pythonic syntax. It spits out something, and out gets PTX. You compile it with PTX-AS. You could compile it with the driver JIT. You could compile it with the PTX-AS that ships with the toolkit. But the key idea is you have full control over the hardware. You are querying the thread ID. You can issue control flow. You can print from the kernel, which we know people love in order to be able to debug their kernel. And not only that, you can also JIT on the host side so that whatever code that you are launching on the GPU side can have full correspondence with whatever you're writing on the host side as well. We'll have full support for Torch and DLPack tensor formats as well, and in the future JAX as well, so that you no longer have to write these ugly PyBinds shims between the PyTorch framework as well as the C++ kernel, right? You can just live in Python, call your kernel with PyTorch tensors, and you're off to the races. And the speed ups that you get in compile times are dramatic. We're talking about more than 100 times faster compile times. A Cutlass C++ kernel that takes 25 seconds to compile today is going to take 180 milliseconds in the future to compile. And you can just imagine how much more auto-tuning you can do for your network. Within the same wall clock amount of time, you can auto-tune over hundreds of times more kernel shapes so that you can pick even faster kernels. So it's not just about JIT times. You can get end-to-end better performance. And speaking of performance, it's within 1% of the Cutlass C++ performance as well. So you're not making any compromises by going to the Python implementation itself. There's a much, much lower barrier to entry because there's no more C++ templates at all. And we know that's a large albatross around Cutlass's neck. So we're very, very happy that a lot more people will be able to have access to the level of performance and control over the hardware that's never been possible before. Okay, and we are also, considering all the talks before this, we're also hoping that LLMs will have a much easier time generating this because of the much larger training token data set that Python has available for us. So how do you get started with all this stuff? We're going to have two really, really good GTC talks for you for this year. The first one is the Python Cutlass 4 talk itself, which is going to be enabling tensor core programming in Python with Cutlass 4. Session IDs are listed over here. But then there's also the sister talk, which is focusing on the Blackwell tensor core, as well as the Cutlass C++ abstractions. And they go hand in hand because the Python framework itself has complete one-to-one conceptual portability across C++. If you have spent time learning Cutlass and Qt for the last 2.5 years, none of that is going to waste. It looks nearly identical between the two, except that you get all of the benefits that I just talked about. We're also going to completely overhaul our documentation. We hear you from the community. Our documentation we can do a lot better on. And with the Python stuff, we're moving to a dedicated web page under docs.nvidia.com, and it's going to have very comprehensive documentation, just like NumPy would, at every single API entry point. So rest assured. And of course, this Python also allows us to have Jupyter notebooks, so we can show you tutorials of how to write optimized kernels for all of the NVIDIA architectures. And there will also be examples that are copy-pastable and ready to go for like Flash Attention 2, gems that target Ampere, Hopper, and Blackwell. Oh, by the way, I forgot to mention, Cutlass 4 will support every architecture starting with Ampere forwards. So there's a large set of architectures you can already target, good to go. If you have a GeForce card, you're also good to go. And with that, that's the end of my talk. I'll just leave a couple more talks over here at GTC that I think you should go watch. And with that, I'll hand it back to Mark.
All right, did people figure out who our super secret guest speaker is? He's in the room, he's sitting in the front. I won't point. But you know, about 18 years ago, GPUs were still fundamentally graphics. Like there was like primarily hardware to accelerate graphics programming. And there was like one person who figured out how to turn this into a general purpose programming platform, basically fast parallel C++ with a project called Brook GPU. And later on ended up inventing sort of a nice, cute little project called CUDA. So without further ado, I'd like to invite Ian Buck to the stage. Thank you.
I think I have a mic if this works. Otherwise, I'll use yours. Hey, thank you, and thank you, Mark. And it's a privilege to be here. I'm sorry it took so long to get me onto the stage. My name's Ian. I thought it would be fun and interesting to talk a little bit. You guys are all about making GPU programming easier and more accessible. I really enjoy, and that's done through libraries, through DSLs, through benchmarks. But the way you introduced GPU mode was, let's just get a better tool, easier to use, and out there more. I couldn't believe that like motivated me from the very, very beginning. So perhaps instead of talking about how much what I'm working on to make GPUs better, I do have a little bit of perspective of how hard it was to program GPUs. So I thought at least I would give a brief history, at least a brief background on what it was like in the very beginning of this whole journey. So yeah, I joined NVIDIA in 2004, but I actually been kind of thinking about I'll say graphics as a compute platform all the way back since my undergrad. I've noticed some Princeton people here. I did my undergrad in Princeton. Thank you. That was awesome to see in the computer graphics lab. I was sitting up there back then, dating myself. There was a lab, actually a lab, with a bunch of machines from a company called SGI, which is no longer around. But they invented a graphics API called OpenGL, and I was a graphics geek, coding and loved computer graphics as an undergrad. But along the way, as I was hacking computer graphics, kind of realized that maybe this graphics thing could be used for more than just playing video games or doing my graphics research. And we actually, one of my first, people always ask me, what was your first like CUDA program? Actually, my first GPGPU program, they called it back then, was thermal diffusion. I had a little simple metal block, and I simulated the thermal diffusion. Then I followed it up with the Navier-Stokes equations, and I actually simulated the full Navier-Stokes equations on a SGI Octane. And the only way you could compute back then was with triangles. Every pass of the PDE solver was one giant triangle that covered the whole screen, and you didn't even have programming back then. It was just OpenGL convolution expressions and trying to do additions and math. And I see Mark Harris here for the first thing. Hey, Mark. He could tell you all these old stories. GPU programming sucked. It was really bad. So this is a slide deck that I did for my SIGGRAPH paper, and kind of talking about like it should be this easy. I just wanted, you guys are doing kind of tensors and matrices. I was just trying to add two vectors. It was way harder. You had to create this thing called a floating point P buffer. That's Microsoft Windows, like this pre-MFC code. It was before there was AMD, there was ATI. It was with DirectX. It was awful. That was just to get like a workspace. And then you had to create some floating point texture. Everything, like it was a floating point texture, but everything was blended for pictures and images. So if you tried to do additions, it would try to like smooth out your texels for you. So all my numbers would just smear across, and it was terrible. And to actually turn that off was a real pain in the butt. You had to write the actual add shader. You had to copy stuff to the GPU. Then you had to render a shader quad. Then you had to read it back from the GPU. And then you actually added two vectors. And that was my SIGGRAPH Lightning talk in 2004. I didn't say anything. I just let it play through. They really enjoyed it. I still enjoy it today. I want to, first off, should definitely want to thank everyone for making the GPUs easier since then. So back then, my PhD, and turned out to be my thesis, was a project called Brook. Let's make this easier was kind of the engineering momentum, but also to think about, hey, how can we use these new kinds of processors, these things called GPUs? Apparently they're fast. They were fast. Actually, they had way more floating point than what CPUs had even back in 2004. They were just really hard to use. I was as a grad student at Stanford. My friends were getting hired by hedge funds so they could like write GPGPU OpenGL and DirectX code because they figured out that the stock pricing algorithms ran really fast on GPUs. It was like a ninja trick. You had to be a PhD in computer graphics and a systems programmer and a domain specialist, and good luck. While there was a ton of, you could actually back then get a PhD by coding and being an expert in this area, my research went into making GPUs easier to program and more available. Started a project called Brook. Brook was a how to write in a way that programmers could understand, programmers could use. It was compatible, but still ran on a GPU, which really only did computer graphics. It was really hard. GPUs couldn't, you couldn't do a scatter. You couldn't write to any arbitrary place in memory. So everything had to be written where the render engine wanted it to go. So it turned into actually a functional-based programming language because you had to code it backwards. You knew where you could write. You could only write to that location, and you had to write your kernel on top of that. But if you go read the Brook paper, you'll see very early ideas around CUDA. It was based on this concept of streaming because it helped with the memory model because you couldn't write, you had to write to this one location. But we did a bunch of stuff. We did ray tracing, we did marching queues, we did FFTs, we did matrix multiplies. I think it's still on SourceForge. That was pre-GitHub. And you can check it out or read the paper. So doing this research, obviously NVIDIA was down the street. I was a grad student at Stanford. And had a great time sort of building this thing, I made it open from the very beginning. And that was really cool. Got a lot of different people interested, and Stanford was a great place for collaboration. I walked across the street to the BioX building, and I worked on molecular dynamics with one of the researchers there. Actually, still to this day, GROMACS was one of the first programs ever, scientific computing programs ever used on Brook. And today, I think still does. I meet with them every time they come to NVIDIA to talk. So obviously, NVIDIA was a big sponsor. They helped me. They gave me a graphics card every once in a while. I think we still do that. I try to do that. And then they came in funded the work. They'd come over and they'd talk to me about it, and I thought they were really interested. Really, I think they were just looking for someone to hire. And 2004, they came by and they said I was basically finishing up my PhD, and they gave me a job offer. Turns out when I got there, they had already started on the next version of the GPU called the NV50, which eventually became the GeForce 8800, way back in the day. And they had the hardware idea and the programming model kind of already baked. They'd read all the papers, they'd seen what people are doing, and they fixed some things. You could write to an arbitrary place in memory now. Yay. You could read. They also had a much more simpler, they could turn off all the graphic stuff and just give you access to the cores, which is great. They also added floating, like real proper IEEE floating point to the core. So we had some real FP32, no FP64, but 32-bit floating point, and all the major C types, which is great. What they didn't have is how to program this thing. So I joined as and I had interned in NVIDIA before. Actually, I started, my first internship was in 2000. So I got a really cool low badge number. But I joined in 04 and joined officially, and started CUDA. When we started CUDA, I got to tell you, everybody thought, hey, let's make the world's next great programming language. And I had all these ideas, and we'd go out and we'd actually meet all the developers and meet all the companies that maybe would be interested in computing. Nobody wanted to learn a new programming language. It was a bad idea. We went with the hedge fund guys and the oil and gas guys and the scientific computing guys. They had programmers. And those programmers really just wanted to use the GPU. They did not want to learn new programming languages, new concepts, new abstractions. As a PhD student, I was offended. So the idea around CUDA was very simple. Start with C and give people the most, like Brook, a really easy way to get access to GPU. And that's why we called it CUDA, because we gave the letter C in front of this thing called UDA, which is the Unified Driver Architecture, which is the thing that made NVIDIA successful in graphics and was the core of our architecture. So C4. And so that's what we did. It was only 2 simple language extensions, the angle bracket syntax and some decal specs, just to say this kernel should run on the GPU, this is how many times you should run, and so I could teach you Saxby in one slide. I really, really wanted to teach you how to add 2 vectors, Saxby in one slide. That was really a good call. So again, make GPUs easier. Joined in 04. We actually launched in 06 with the hardware. Lots of fun stories there. And it was exciting to the research community. It did not take off immediately. Despite the success you may see today, it actually took about 10 years for us to actually build a real business around computing. This is just because the people, getting it out there, getting access to GPUs was hard. I'm sorry that getting access to GPUs today is hard still. But we did one important decision back then, which was make CUDA available on every GPU. I think we kind of take that for granted for now, but that was a really big, important decision that I didn't make, my boss made. It's like, we should put this capability in every single GPU, including the gaming GPUs. It was a painful decision. Adding FP32, adding all that compute logic, adding all that silicon area, and supporting every GPU going all the way back to 2006 and that GeForce 8800 to this day, huge cost. It actually, at one point, there's stories of NVIDIA's stock price crashing because it was just so how expensive it was to build these chips. It was the best decision, I think, for CUDA that could have ever been made, because anyone who had a gaming laptop, a gaming PC, something, could download free CUDA and just run with it. So make it easier, make it more accessible. Totally the mission. Joining NVIDIA, I had to actually create a couple of useful things. First thing was a FFT library and a BLOS library and a math.h. I got to compile the person and sort of build it up from there. Fast forward, it took about 10 years. Lots of successes along the way, built up in supercomputing. Basically, everyone who really needed the time and energy to actually accelerate and do work, get compute to have an outcome, and could take the time to build these things, was very successful, of course, until the AlexNet moment hit us. A couple of things when Alex, he was so shy, he sits in the back. If you've met Alex, he's a very humble person. He was actually working, NVIDIA had, the story around AlexNet is we were certainly, this is about, I can't remember, 10 years in, 8 years in. We were obviously working with all the academic communities, folks exactly like yourself, and with Fei at Stanford and the ImageNet competition. And they were kind of stuck in computer vision for at like 70% accuracy, 60% accuracy, really not enough for like commercialization. And Alex had this idea of a convolutional neural network where it's not a fully connected network, was an idea. And he saw that the math he was doing for his convolutional neural networks was the same kind of math that we had done for HPC and scientific computing. He downloaded CUDA. He had bought I think it was an RT. The names have now cycled around a few times, just for the record. I think it was an RTX 580 or two of them, put them in a PC, downloaded CUDA, and sure enough, it went fast. What normally would take an entire semester, he was able to do in a single month. There was another guy named Ilya who was also working on a similar problem. His work took like, I think an entire 6 months or something like that, and got it down to 3 months and then to 1 month. It's a terrible way to get a PhD in AI, but we made it a lot faster for them, made it easier, and as a result, he crushed the competition and immediately took off. What was like inside NVIDIA, we were helping, called CUDA CovNet, was the original, I think the first AI framework, pivoted the company, find how can we make this easier, better. That was the beginning of cuDNN, and making a library, just like a library that could make it easier, more accessible, so you guys didn't have to write all the damn kernels. I'm sorry that mission failed. I think Triton's super cool. I think finally we have a DSL that can actually build kernels. I know it's not the only way to build kernels. I like Cutlass. I like Triton. Every way, different ways, and now we actually have an ecosystem, and actually Python's a much better way of doing it, of DSLs that can help us explore how the hell to build fast and efficient kernels. Certainly, the other big moment that happened for us, I can tell you about, which is BERT. BERT was a really transformative time at NVIDIA because basically it's unsupervised learning. You could download the internet or a page of the internet, remove some words, ask the model to fill in the words, see if it got it right. That process did not involve a human. And there's a lot of pages on the internet. So that caused an explosion. by this point. Our GPUs are getting recognized by Google and others, and people are swarming this. But once you created a way of learning that was unsupervised and scaled to the scale of the internet, you can imagine this was the birth of large language models. This was also the time where we're starting to build more tools, trying to figure out how to make inference better. The start of TensorRT, the start of other expanding the number of libraries. It's around when Cutlass starts getting created, building more and more libraries for accelerating models like BERT, and all the different language models that happen after that. Finally, DeepSeek, like, damn, those guys really wrote some amazing code. If you look at the kernels, and you look at what they've done, they turned every knob and cranked and exploited every opportunity to make things run fast. Not just their latent attention methods, which are really cool, but the way they use the RDMA features, by pulling the data right out of the GPU and getting it across to the next one, to take a model that's 671 billion parameters with 61 layers and 256 experts with a shared expert, and getting that to work across InfiniBand takes me back to the original GPGPU days. And just not being afraid to go down in the weeds and get the kind of performance that they do. It is great to see this community still thriving, finding ways to optimize, to exploit performance, not being afraid to go down stack, up stack, and then again, we'll all learn from it and figure out how to make, like I've seen here, tools to make it easier and more accessible. I think I get to play with a lot of hardware now, so hopefully you guys will get to enjoy it as well. I'm really excited to see B200 and Blackwell in the market, like the hackathons that we're having today. You guys are I already have folks who be running Llama on racks today. I just saw some benchmark performance numbers by one of the cloud guys. They got this working on the MLPerf Llama benchmark at 888,000 tokens per second on Llama. I think that's like, I think that, so I did the math. I believe that is the entire Harry Potter series in like a second. And it just keeps going. So this is, I now get to do it both. I spend probably less time in CUDA and library strategies than I'd like, but I think it's an opportunity I get to also, while I help this, I can also figure out how to make that easier to program, or this switch, or that network, or these pieces come together. And I really enjoy it. So thank you for inviting me. I'm happy to answer or take any other questions. I will add with one more thing. The early GPGPU days were super fun. You have a lot of these people here. A lot of stuff was hacked on the GPU. It's not just about AI. I still get to talk about molecular dynamics, plasma physics, and all the other use cases. And some of my colleagues back in the day are still here. In fact, in 2003, I got to work with a guy named Patrice Simard. And this is back when the early painful GPGPU days. There was something called direct compute. It was written in C#, it's an interesting language. And then I don't know, the get and set operator is pretty cool. After that, I'm not sure. And then you really don't want to use it for graphics, but we tried. But I wrote a GPGPU program. It was a 2-layer, fully connected neural network on MNIST, and ported it in direct compute with C#, in fact, and ran, I think, and published the paper actually in 2003, which I think is the first GPU AI program ever written. And if you go find it, it's pre-archived. It's in there somewhere, and yes, it was faster than a CPU. Anyway, thank you.
Oh. Okay, wow. So Ian's interested in taking questions, but I need to jump the queue for a second, which is 10 years, no product market fit. I'm imagining some NVIDIA director being like Ian, the problem with this is that it's not simple. Like customers want a make fast function that just parallelizes their code. And so how did you manage to have conviction that you needed to really build a programming model when you didn't have product market fit for so long?
I was very fortunate to have a founder CEO